In the interval 0 to 360, the equation sine cubed of x plus cos squared of x equals 0 has how many solutions? 0, 1, 2, 3, or 4. So yet again, we have an equation which involves a few sines and a few cosines, and yet again we're solving it qualitatively. All we need to do is recognize how many solutions there are, not what those particular solutions are themselves. So I think the best way to do that in this case is to minus the cosine squared over to the right hand side, such that we can write the equation as sine cubed of x equals negative cosine squared of the x. And now I have a left hand side which is equal to a right hand side. And I can now go about plotting both the left hand side and the right hand side on the same graph, and then recognize where those graphs intersect. And the number of points of intersection is going to tell me how many solutions I have between 0 and 360 degrees. So let's focus on the left hand side. You can see we have sine cubed of x. So to draw that, you might want to think about what sine of x looks like. Sine of x starts off at the 0, goes to the 1 at 90 degrees, back to the 0 at the 180 degrees, down to negative 1 at 270, and then back to the 360. Back to the 0 at 360 degrees. And what you want to do, you want to think about what's going to happen when we take all the y values here and we cube them. Because that's ultimately what I want to do. This is the curve of y equals sine of x. Whereas I want to draw the curve of y equals sine cubed of x. So you want to think about taking all the y values on this green curve and cubing them. Well, when you do 0 cubed, you're going to get 0, so that's definitely going to be a point. 1 cubed is going to be 1, that's definitely going to be a point on my new curve. 0 cubed is 0, negative 1 cubed is negative 1, and 0 cubed is 0. So all these blue points would lie on the curve y equals sine cubed. But there's a few more insights you can gauge here. Number one, sine of x always has a magnitude which is less than or equal 1. So when you take the magnitude of this, it's always less than or equal 1. And because of that, when you cube it, the magnitude of sine cubed of x is always going to be less than or equal to the magnitude of sine of x itself. And it's only going to have equality there when the output is 1, and that happens at 90 degrees. And or negative 1 would be at the 270 degrees. So for that reason, the sine cubed of x is going to hit the sine of x at the 90 degrees. And any other points, the magnitude of the sine cubed is going to be less than the sine of x. And that means the sine cubed of x graph is going to be between the green curve and the x-axis when we come to draw it, because we need the magnitude of these y values to be less than or equal to the magnitude of these y values. There's a few further insights to be gauged here in that sine of x, when x is very small, you can make a small angle approximation for sine of x. When x is very small, you can write sine of x as approximately equal to x. And you can kind of see that on the graph here as well. If you imagine zooming in to this area here, it's going to look pretty much like a straight line. If you zoom in close enough, it's going to be a straight line, and the gradient of that line would be 1. So we can say the graph of y equals sine of x approximates the graph of y equals x when the x is close to 0. So imagine how that looks on the graph of y equals sine cubed of x. Well, if sine of x approximates x when x is close to 0, sine cubed of x is going to approximate x cubed when x is close to 0. And we know what x cubed looks like. It looks a bit like this when you draw it on a y equals x cubed graph. You get a point of inflection right here when the x equals 0. So when x is close to 0, sine of x is going to behave like sine cubed of x is going to behave a lot like x cubed, and you're going to get a point of inflection right here. So the cubic graph is going to be looking a bit like this. And now we can just join up the rest of the points, right? We know it's going to go to 1 at the 90 degrees because 1 cubed is 1. And then it's going to behave in a very similar fashion for the rest of the points. So sine cubed is going to come down. It's going to pass through the 180 there. And then again, it's going to go down to the negative 1 because negative 1 cubed is negative 1, passes through there, and then comes back up and passes through there in that fashion. So this is what sine cubed of x looks like between 0 and 360 degrees. So let's go ahead and take a stab at drawing the right-hand side now. Let me do it on a different graph. The right-hand side is the negative cosine squared of x. Let's start off by drawing the graph of y equals cosine of x. It's going to look a bit like this. So cosine of x goes to 0 at 90 degrees, and then it goes to -1 at the 180, back through 0 at 270 degrees, and then back to 1 at the 360 degrees. This is what y equals cosine of x looks like. Now imagine taking this graph and again squaring all the y values. As opposed to cubing them, we're going to square them this time. Well, right here is 1 and right here is -1. So when we square the y value of -1, it's going to become +1. So we know +1 is going to be on the graph of y equals cosine squared of x. We know 0 squared gives us 0, 0 squared gives us 0, and 1 squared gives us 1, and also 1 squared gives us 1. So all these blue points we know are going to exist on the graph of y equals cosine squared of x. And by similar reasoning to the last question, the magnitude of cosine squared of x is always going to be less than or equal to the magnitude of cosine x. And it's only going to be equal, these two magnitudes are only going to be equal when the output of the cosine is 1 itself, because that would just say 1 equals 1. So for that reason, the cosine squared of x is always going to be between the green curve and between the x-axis, such that the magnitude of it is less than cosine of x itself. Moreover, when you're close to the 90-degree point here, again, the graph behaves like a y equals -x graph. It has a gradient of -1 going through here when you're working in radians. So that's very similar to y equals -x. And when you square that, you get y equals -x all squared, which is the same as +x squared. So it behaves like a quadratic minima right here. So here's what it's going to look like. Scooting down, quadratic minima right there, and then scooting up and kind of like a quadratic maxima right there. And then scooting down, quadratic minima, and then scooting up and quadratic minima. That is what y equals cosine squared of x itself looks like. But the right-hand side here, it was the negative cosine squared of x. So if we negate all the y values here, that corresponds to a reflection in the x-axis. So -x squared, negative cosine squared of x is going to look a bit like this by comparison. So this is the red curve. This is the negative cosine squared of the x. Y equals negative cosine squared of the x. So all that remains to do is compare this red curve of y equals negative cosine squared of x to this blue curve of y equals sine cubed of x and see how many times they cross each other when we draw them on the same graph. So let's take this cosine squared. You can see it goes up, down twice. Let's go ahead and draw that over here. Looking a bit like this. This is what the negative cosine squared looks like. A bit like this, going down, hits the 0 there, then comes back up. And there we go. Right, that's my negative cosine squared of the x. And you can see immediately it's going to pass my sine cubed of x. That was the blue curve. It's going to pass it at 2 points. One point is right here, and one point is right here, between the 0 and the 360 degrees. And therefore, we're going to get two solutions. This point here, and this point here. So by that reasoning, purely graphical, qualitatively, there's going to be two solutions to this particular equation between the domain of 0 to 360 degrees.